So lesson 56 is on counting principles, permutations, and combinations. So we did all of this in Algebra 2, but we're going to recap it today. So I always use my nieces and nephews, Eleni, Bridget, CJ, and Devin, because my sister-in-law, for some reason, named her kids with the initials A, B, C, and D. But they're always in my probability problem. So you see these names, these are my nieces and nephews. So, what?
Why is my name?
I know. So I should put yours in there. All right, so Eleni, Bridget, CJ, and Devin are running a race. How many ways can they place? So do you guys remember how we did this before? We did basically what I call the slot method. So it's like if you're going to get first place, there are 4 people that could cross the finish line first. Once that person crosses the finish line, so let's say Eleni crosses, then Bridget, CJ, and Devin are left as 3 for the next spot, right? For second place, there's 3 possibilities. And then we have 2, and then we have 1. Do you guys remember this? So 4 times 3 times 2 times 1 ends up being 24 ways that they could place. So you can list all of those possibilities out. So you can do A, B, C, D, A, C, B, D, A, D, B, C. Like you could list all of the possibilities. There would be 24 of them, okay? So it says how many access codes can you have if the first 2 letters must be first 2 characters must be letters, and the last 2 characters must be digits from 0 to 9. So we have 0 to 9 here, and we have 0 to 9 here. And we can have letters, so I'm guessing we can do A to Z. I didn't really say. Okay, so letters A to Z for the first 2 spots. Digits 0 to 9. Now it says, assume you can repeat the letters. So in the first spot, I have 26 possibilities, A through Z. If you guys all know there's 26 letters in the alphabet. Maury every year is like, how many letters are in that? Like, Maury. He like forgets. He's like, I don't know. At one point I thought it was like 24, and I just keep forgetting. All right, so 26. And then you can't repeat the numbers. So can I still have 26, or is this going to be a 25? 26. It's going to be 26 because I can't repeat the numbers, but I can repeat the letters, right? So I have 26. Now for 0 to 9, how many digits are 0 to 9? 10, yes, because we count 0 as well. So we have 10, and then what? 9. Do you guys remember this? So we do 26 times 26 times 10 times 9. And we end up getting 60,840. A lot of ways, right? All right, so we do something called stewardship, whereas a lot of schools do like student council, well, not student council, but like class officers. So I was the class treasurer because I was good at math. But we don't have a class treasurer and class president and so on. Okay, so we have stewardship. And in stewardship, everybody has the same duty, right? They're all on the, like they go to the same room. There's not like one that's more important than the other, right? So it says there are 5 sophomores that want to be chosen for 2 stewardship positions. So I'm not going to do this one like 5 times 4. I can't do that. Explain to me why I can't. Yeah, Greta.
Because there's not a specific spot that is there. Like you're not placing, it's all the same.
Yeah, it's not like first place. It's not like, ooh, they won first place and this person got second place, right? So if I take my letters A and B, like Eleni and Bridget, and I talk about those, like Eleni being in the first spot and Bridget being in the second, this combination, like A, B, and BA, is actually the same for stewardship, right? They're both, the 2 of them are chosen. They're both there. Does that make sense? So we end up dividing by the number of repeats. And the way you can repeat 2 people is you can divide by 2, right? Because I could have AB or I could have BA. So it's like we could do 5 times 4, but then we would divide by the number of ways to arrange 2 people, and we would divide by 2 times 1. Okay, this is what we call a combination. So this would be a combination of 5 people putting in 2, not necessarily positions, but 2 people are chosen from those 5 people. So I often read this as 5 choose 2. Okay, now there is a formula for that, which we'll talk about in a second. But I like to think of it like that. Like I put them in their places and then I divide by the number of repeats. So we get 10 possibilities. Yeah?
So 5 choose 3 would be 5 times 4 times 3 over 3 times 2.
Yeah, you could do 5 times 4 times 3 over 3 times 2 times 1 would be 5 choose 3. But you know what's kind of cool about combinations? I don't know if you guys remember this. Notice how those cancel? Look, don't I still have 5 times 4 over 2 times 1? So 5 choose 3 is actually the same as 5 choose 2. So let's think about this in, like real life. Okay, I have a really awesome club because I'm like the coolest teacher ever. I'm really not. I'm like the nerdiest teacher in the world. But I have a really awesome club and everybody wants to be in my club. I don't know what it is. And I say that there's 5 people that want to be in this really cool club. That's not really cool then, isn't it? Only 5 people. There's 5 people that want to be in my cool club. But I only have 2 spots for this really cool club. Okay, choosing 2 people to be in my cool club, isn't that the same as choosing 3 people to not be in the cool club?
Yeah.
Right, so 5 choose 2 is actually the same as 5 choose 3 because you're saying, if I have A, B, C, D, and E, and I choose A and B to be in the cool club, well, that's the same as picking these 3 to not be in it, right? Does that make sense? And then if I choose like A, D, then I'm choosing B, C, E to not be in it. Okay, so there's a little bit of like symmetry to it. Okay, so sometimes it's easier, like when Greta was saying, like if you have 7 choose 6, I don't want to do 7 times 6 times 5 times 4 times 6. Does that make sense? I want to do 7 choose 1. To me, that would be faster, right? So it's like 7 people for 1 slot, divide by the repeats. Well, that's just 1. So it's 7 ways to choose 1 person. Does it make sense in your head why there's 7 ways to pick 1 person to be in your cool club? Yeah, okay. So, going on. So one of these is called the fundamental counting principles. This is what I call the slot method. So if you hear me refer to the slot method, it's just you're filling in these different slots. So it says there are A ways to do event number 1, there's B ways to do event number 2, C ways to do event number 3, and so on. So the total number of ways to do those would be A times B times C. Okay, you just take those 3 things multiplied. Okay, now permutations. So I always told you to think about positions, places, presence, right? This is where your order matters. Okay, so this is where it matters if you're president versus vice president versus secretary versus treasurer, right? It matters if you're running a race and you get first versus 10th. I would be really mad if I got first and they gave me a 10th place ribbon. I'd be like, where's my medal, right? So this is going to be permutations. So every outcome, I'm giving you guys my evil eye. Every outcome has a certain order. So these have order. All right. Yeah, totally Nick. Nick's the one talking. All right, n factorial over, what happens is it's n minus r factorial. Okay, you guys know this formula? You don't have to memorize this formula. You know what this means. Okay, so I just said if there were like 8 people and they're running a race and there's a first, second, and third place for that race, and I don't care if anybody gets 4th, 5th, 6th, 7th. There's no prizes for those, so I could care less where they get there. That would be 8 times 7 times 6, right? We just did that. That's the fundamental counting principle. Okay, what happened to 5, 4, 3, 2, 1? I don't need those, right? Isn't that the same as 8 factorial over 8 minus 3 factorial? 8 factorial over 5 factorial? Do you see how the 8 times 7 times 6 and then the 5, 4, 3, 2, 1 cancels with the 5, 4, 3, 2, 1? Do you get where this comes from? Okay, that's the formula. Don't sweat it. Don't try to memorize this formula and mess it up. Just think about permutations as being the slot method. So still use the slot method. Okay, so combinations. So I want you to think about clubs and committees. I want you to think of groups of items. If I have a group of items, it doesn't matter what one's first, second, third, fourth, fifth, right? If I have, I don't know, community service club, nobody cares who's like number 1 in community service club. Everybody's in the club together. Everybody's working together, right? That's going to be a combination. Okay, so it says if there are n items that must fit in R positions in any order, then the total number of ways that this can happen is going to be n factorial over, you still have that n minus r factorial, but you divide by the number of ways that things are repeated. So we divide by r factorial. Okay, so that's what I was doing before. So if I have 7 choose 4, I can do 7, 6, 5, 4, 4 places that I'm filling, over, but it's like if I have 4 people, how many ways can I arrange the 4 people's names? Right, if I have 4 people? 4, 3, 2, 1. So I divide by 4, 3, 2, 1. It's like saying how many ways can I place in a race? Does that make sense? So then the 4 and the 4 reduce out, and you can go from there. See how it's the same as 7 choose 3, though? All right, so that's the best way to think about these formulas. Okay. There is a button on your calculator. Do you guys remember how to do it on your calculator? So if I wanted to do 7, choose 4, I first put 7 in my calculator. Then I hit math. I go over to PRB, or probability. And then I go down to NCR, or NPR if I'm doing a permutation. And I hit 4. So 7 choose 4 is 35. And you can see if you start reducing this down, that 3 and the 2 reduced with the 6, do you guys see how we get 35? It's almost faster to do by hand sometimes. Did you do 7 permute? So do the C. 7 NCR. Yeah. All right, so which of these two numbers is bigger? So if I talk about permutations versus combinations, and I'm saying I have my Eleni, Bridget, CJ, and Devin, and I want to find the number of ways to order their names, right? Pick 3 of them and put them in a certain order, let's say. Is that more than the number of ways of selecting 3 of them? Yeah, selecting 3 of them. If I have 4 kids and I'm selecting 3 of them, I'm selecting the one kid to not be hanging out with me. You don't get to hang out with Aunt Jenny. They just get to stay at home. That would be sad. So there would be 4 ways to do that, right? Does that make sense? 4 choose 3 is the same as 4 choose 1, which should be 4. But if you talk about 4 permute 3, that would be a situation where you say something like, hey, I'm going to pick 3 kids to hang out with me today. One of you gets to pick the restaurant we go to, one of you gets to pick the movie that we go to, and one of you gets to pick dessert. Does that make sense? Those kids might have a preference. Like my nephew would be like, I want to watch Star Wars, right? He'd be the one that wants to pick the movie. And if he didn't get to pick the movie, he would be upset. Do you guys see what I'm saying? There's more possibilities when you order them. All right, so number 1. So a baker has 4 different types of frosting, 3 different types of sprinkles, and 5 different flavors of cake. How many different types of cupcakes can be created if she uses 1 frosting, 1 color of sprinkles, and 1 type of cake? Well, that's just accounting principle 1, right? So it's going to be, we talk about frosting. We have 4 different types of frosting, 1 type of sprinkle, so we had 3 choices there, and 5 different flavors of cake, so we had 5 choices there. So we end up getting 12 times 5, which is 60. All right, Stephen has 6 pairs of pants and 8 shirts in his closet. He wants to wear a different combination each day without repeating or buying new clothes for as long as possible. So how many ways can you do this? All right, so let's see. You really want me to put you in a story problem, don't you, Cade? You are! In number 5, Cade and Zach are going on dates. So exciting. All right, so Stephen has 6 pairs of pants and 8 shirts in his closet. So basically he wants to wear a pair of pants and a shirt. I guess he could wear like more than 1 shirt, but let's just say he's wearing 1 shirt. So what are we doing? We're saying 6 choices for pants, 8 choices for shirts. That's going to give all the different combinations of shirts and pants that you could wear. So it ends up being 48. All right, a certain state has a license plate that have 2 letters followed by 4 numbers. Letters and numbers cannot be repeated. So how many different license plates could they have? So if I can't repeat them, I have 26 choices for the first one, but I only have 25 for the next one, right? And numbers, how many choices do I have for the first one? 10, and then 9, 8, and 7. So we end up getting 3,276,000 license plates. All right, this is a tricky one. This is a classic probability problem. We could maybe do this experiment later if you want. So 20 people in a classroom shake hands with each person exactly 1 time. How many handshakes occur? Any guesses? How would I do it? 20 times 19, maybe? Is that what you're saying? So 20 times 19, very close. Okay, so the reason it's not quite 20 times 19 is because Anna Catherine shaking hands with Paloma is the same as Paloma shaking hands with Anna Catherine. So we have to consider that. So it ends up being 20 people choose 2. Think about that. If I have 20 people in the classroom and I want to find how many ways I compare them, And then when I'm pairing them, they shake hands, right? That's how it works. We're finding the number of ways to pair 20 people. Okay? So that's basically doing what Greta said, which is 20 times 19, but we're dividing by the repeats, which was 2 times 1, right? 2 ways to arrange 2 people. So we end up getting 190 total. So you can do that in your calculator, or you could do it off to the side there. All right, a group of friends decide to go to the movies. So Kate and Zach bring their dates, and 2 of their buddies tag along. You guys are claiming the buddy spot? All right. When the friends arrive at the theater, there are only 6 seats. How many ways can the 6 friends sit in a row? So if you have 6 people and you're lining them up in a row, how many ways can you do it? 6 times 5 times 4 times 3 times 2 times 1, right? Which is the same as 6 factorial. Do you guys remember the factorial button? So factorial button's under probability as well, and it's choice 4. It ends up being 720 ways to arrange them. A lot of ways, right? Okay, but what if Kate and Zach want to sit next to their dates? Okay, this gets a little complicated. Okay, here's the tricky part. Okay, if they want to sit next to their dates, that really means that you kind of have like 4 things that you're rearranging. So you have Kate and Kate's date. You have Zach and Zach's date. You have friend 1 and friend 2, right? Does that make sense? And you can rearrange all these people. All right, but I'm going to put C1 and C2 because Kate and Kate's date are different people, right? So I'm going to think of them at first as 4, right? Okay, so we're going to do that first. If we had 4 people and we arrange them in as many ways as possible, we end up getting 24. So that doesn't seem like a lot. But here's the trick. This is where probability gets really confusing because there's like so many, like case 1, case 2, case 3. This is what we need to think about. So I could have Kate and Kate's date sitting in that order, and then I can have Zach and Zach's date sitting in that order, or I could switch them, right? So we need to think about all of those. Yeah, Greta.
So do you multiply by 2?
Yep, so if I have Kate and Kate's date, so if I have that order, then I can now switch them. So it takes all of my outcomes and it multiplies them by 2. So I have 48, right? But what else? There are more. Yeah, it's kind of confusing because now you have to think about, well, what about Zach and Zach's date? So here's what I'm going to do. So let's not think of it like this necessarily. Let's think about it. If I had C1, C2, Z1, Z2. Okay, of those 4 people. So C1 is left, C2 is right, Z1 is left, Z2 is right. How many ways can I arrange? I don't know how to best say this. It's not like I want to. So I could have, let's just list these out. So I could have C1, C2, and then Zach and his date could switch, right? Z2, Z1. I could have C2, C1, Z1, Z2, right? And I could have C2, C1, Z2, Z1. Do we agree? There's 4 ways. Okay, so what do I do? 24 times 4. Did that just kill you? Yeah.
But what if the friends sit in between the 2 of them?
Oh, what if the friends sit in between? I think we have that accounted for because the dates are the 2s, right? So that would be this situation, right? But they can't switch. Like, they're not going to switch, right? Because they want to sit next to their date.
I'm not sure if it matters, but what if Zach and his date sat on the left instead of the right? Like, would that?
Ooh, good question.
Sorry.
That's true. What if Zach and his date sat on the left? That's true. So what do we need to multiply by? So it does matter. So now we say, well, these whole things could switch for all of these, right? So multiply by 2, right? Because then you could have those choices as well.
Is that not included in the 4 by 3? 4 times 3 times 2 times 1? Because it would just be the same as
Oh, you know what? That is already included. You're right. So it is 96. Oh, probability. Did you guys see what Hallie's saying? She's like, oh, but that's already included because we already did the 4 times 3 times 2 times 1, right? So we already have those switched as well. Good thinking. So it's 96, yeah. Ooh, that was a hard one. So fun. All right, so there are 6 points equally spaced around a circle. So I'm going to have 1, 2, 3, 4, 5, 6. I feel like I'm doing roots of unity again. So how many quadrilaterals can be formed by joining these points? Okay, technically I can join any 4 points. You see it? Any 4 points that I join will create a quadrilateral. It's not like I have 4 that are in a line. If I had 4 that are in a line, that's trouble. That's not going to be a quadrilateral. But we don't have that because they're all equally spaced around the circle. So how do I do that? How do I take those 6 points and say, how many ways can I select 4 of those points? It's a combination. It's 6 choose 4, which is the same as 6 choose the 2 that are not included, if you want to write it that way, which would be 6 times 5 over 2 times 1. It'd be 15. So you can do 6 choose 4 on your calculator, or you can remember all these tricks for finding them by hand. Okay, so suppose you have the following dot diagram. How many triangles can be formed by joining 3 points?
Good question. Is it just the same 6 choose 3?
Okay, so we think 6 choose 3. That's close. It will give you most of it. So 6 choose 3, if I want to find that by hand. 6, 5, 4, 3, 2, 1. What is it going to be? 20. Okay, there are not 20 ways. There's less than that.
Because
Some of them hit more than, what do you mean?
like if you start with the right, the top right,
Uh-huh.
and go all the way to like the far left, and then go down, like that.
Oh, yeah, I see what you're saying. I think we would still consider that to be these 3 points, though, creating the vertices. But part of what Olivia was saying right there. Look at that. So she's saying it went through more than 1 point. So I agree with that. That's a line. Okay, are there any other lines created? This one, right? So how many things do I need to subtract out? 2. So subtract out the ones that formed the 2 lines. So it should be 18. All right, so we're playing some poker. I have 52 cards. I deal you out 5 cards. How many different hands could I have? Yeah?
52 times 51 times 50 times 41.
Divided by 5, 4, 3, 2, 1. So you guys see, so she's saying slot method, but it's not quite slot method because they're in my hand, and I'm OCD, and I always rearrange my cards, and I put them in certain orders. You don't have to do that, right? It doesn't have to be in a certain order. They're all in one hand, right? It's like a group of items. So this is a combination. So it's going to be a combination of 52, choose 5. If you ever see me, sometimes I write, like you could write 52C5 like that as well. Sometimes I write it like this. I try not to because people get confused and I think it's a fraction. But that also means combinations. Have you guys seen that notation before? Did I show you that last year? All right, so anyway, so we're doing 52 choose 5, which is a large number. Every person that's ever done probability knows this number. Now, I don't ask a lot of card game questions because I found over the years you guys don't play as much cards as when I first started teaching. I don't know, maybe there's more fun things to do on the internet, I guess. So I'm always like, how can you get a straight flush? And then people are like, wait, what's a straight flush? So I'm not going to ask you a question about cards, but I could ask you something like that. You'd be able to do that. All right, so from a group of 20 people, 12 jurors must be selected. How many different ways can the jury be selected? Does the order matter? No. So it's going to be 20 choose 12, right? Again, another one I would probably just do on the calculator. It's a 5. So 125,970. All right, do you guys remember the arranging the letters in a word? Kind of. So if I had, I'm trying to think of one of your names, Ben. If I had Ben's name, that's such an easy name. We're going to use your name, Ben. And I talked about arranging the letters in Ben's name. How many ways could I arrange the letters in Ben's name? If B, E, and N were running a race, there'd be 6 ways, right? You'd have 3 for the first one, 2 for the second, 1 for the last. Does that make sense? So it's 3 factorial. All right, but what if I had the word Ben? Like, I don't know, I can't even think of it. So if I have that, or if I have Jeep, that's a better one. If I have Jeep, how many ways can I arrange that? 6, you think? Because you're thinking of those E's as being like the same. You can't like order them. So what happens is it's actually 4 factorial divided by 2 factorial. So it ends up being 12. And you can test it out. It would end up being 12. But yeah, E and E, like it doesn't matter which order they're in. So it's because there's 2 E's. So if I had Jeep, I could have J-E-P-E, Jeep, E-P. I should go in some kind of order. I'm not going in any order. That's bad.
So I mean, like, how do you know it's 2?
Because there's 2 E's. So we divide by the number of ways those E's could be arranged, right? Right? We divide out by the repeats, kind of. So for Elijah, we have 1, 2, 3, 4, 5, 6 letters. So I started out with 6 factorial. Are there any repeats? No. So it's just 6 factorial, which is 720. Shh, guys. All right, how about beekeeper? How many letters? Are there 9 total letters? Over 5 factorial, exactly. Oh, geez. I hit all kinds of buttons. All right, 9 factorial divided by 5 factorial. Anybody beating me? Yeah, 3024. Okay, so let's go into some probability. I know, it's never ending. So find the probability of each of the following events. So tossing a head on one toss of a fair coin. What's the probability of getting heads? Yeah, 50-50, half, right? Tossing 2 heads in a row on 2 tosses of a fair coin. Think about how many outcomes I could have. I could have 4. I could have heads, heads, tails, tails, heads, tails, tails, head, right? Does that make sense? 4 outcomes. So getting 2 heads in a row is 1 out of 4. So if you needed to draw a tree, do you guys remember that? This shows every single outcome. So I could have heads and heads, I could have heads and tails, I could have tails and heads, and I could have tails and tails. Tossing 2 heads in a row on 3 tosses of a fair coin. Ooh, that's hard because it's saying 2 heads in a row, but I have 3 tosses. So I could have like tails, heads, heads. I could have heads, heads, tails, right? So there's 2 out of how many? 8. But should we count also? Do you think 2 heads in a row, does that also count like 3 heads? I don't know. I didn't really specify. There's still 2 in a row, right? So I think I would say 3 out of 8. So I could have heads, heads, tails, heads, tails, heads, heads. Or I could have heads, heads, heads. Those are the only possibilities, right? Drawing a king from a standard deck of 52 cards. How many kings are there in a deck? 4. So 4 out of 52, which reduces down to 1 out of 13. Rolling a sum of 3 on a single roll of 2 fair dice. So how many outcomes do I have if I roll the dice? If I roll 2 dice? Think about on one die. 6. On the other die, I have 6. So together, all those combinations would be, nope, 36. Do you guys remember a big, long chart I made you guys do last year? Where we had 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. There ended up being 36. All right, so we have 36 possibilities. How many ways can I get a 3? I could have a 1, 2, or I could have a 2, 1, right? So 2 out of 36, which is 1 out of 18. Ooh, rolling a sum of 3 on 3 fair dice. Yeah, Greta?
Oh, no.
You got it. If I have 3 fair dice, what's the only way that I can get a 3? All ones, right? Okay, how do I get all ones? So there's one way out of 6 times 6 times 6, 216, yeah. Guessing all 5 numbers in a state lottery that requires you to pick 5 numbers from 1 through 50 inclusive, meaning including 1 through 50. So how many numbers are there that we're picking? So there's 50 numbers. And picking all 5 numbers. Okay, when you do the lottery, I don't know if you guys know this, but like they pull the little balls out, like Powerball, they pull them all out, and then they put them in order as you're reading your ticket. So don't worry about the order, it's just a group of numbers. Right, so you don't have to be like, oh, I said 24 and it was my first number. It's not like that. It just has to be one of the numbers. Does that help? So how many ways do I get all of them right? How many winners are there that get all of them right? Well, there could be more than one winner, right? But how many winning tickets are there? But still, I'm saying the same thing, aren't I? There's only one way to have that winning set of numbers, right? Out of how many? How do I find it? Not 50 factorial. 50 choose 5, right? Do you guys see why it's 50 choose 5? I have 50 numbers and I'm selecting 5 of them. Oh man, I did 5 choose. That doesn't work. It's a really big number. So it's 1 over 2118760. So 1 out of over 2 million ways. All right, so we're almost done. So let's do Venn diagrams and tree diagrams. So it says 3 identical cookie jars are on the counter. Jar A contains 1 chocolate chip cookie and 4 peanut butter cookies. Jar B contains 3 chocolate chip cookies. Jar C contains 2 chocolate chip cookies and 1 peanut butter cookie. We select a cookie at random. Draw a tree diagram. So I think the first thing is I'm picking between the jars, right? So I think I would say my first choice is I'm either getting A, B, or C. What's the probability that I would choose jar A? 1/3, right? So if you want to put these little probabilities on the branches, you can. Now with jar A, I have chocolate chip and I have peanut butter. And for jar B, I have chocolate chip. And for jar C, I have chocolate chip and peanut butter. Does this scare you, Ben? It's like what's the probability that Ben will choose jar B and not die? So, peanut allergy. So let's see. So with jar A, we have 1 chocolate chip, we have 4 peanut butter. So I have a 1/5 chance of getting the chocolate chip once I've chosen jar A, right? And I have a 4/5 chance of getting the peanut butter. For chocolate chip for B, I have 4 out of 4. Isn't that just 1? That's a 4/5. They got a little messy there. 4/5. That's just 1. All right, how about jar C? Looks like a 2/3 chance of getting chocolate chip and a 1/3 chance of getting peanut butter. So that's our tree diagram. So our question is, what is the probability that we select a chocolate chip cookie? Okay, so it says if they were all in the same jar, it would be 7 out of 14 because there's 7 chocolate chip cookies out of 14 total. However, since they're in different jars, we have to do jar A versus jar B and so on. So let's look at it. So for drawing a chocolate chip cookie, how many different routes could I get chocolate chip? This route. What's the probability that I went this top branch? I would need 1/3 multiplied by 1/5. That's a 1 out of 15 chance that I choose that one cookie there. All right, how about this route? That would be a 1/3 chance, right? Because if I pick jar B, then I automatically have a chocolate chip cookie. Right, and then what about this route? That would be 1/3 times 2/3, which is 2/9 chance. So we're going to add 1 over 15 to 1 over 3 to 2 over 3. Oh, that seems weird. 2 over 9, geez. Why did I do 2 over 3? I was like, that's more than 1. That can't work. 2 over 9. So 1 over 15 plus 1 over 3 plus 2 over 9. So I end up getting, as a fraction, like if I got common denominators, I would have 28 over 45, which as a decimal is like 0.62 something, like a 62% chance of getting chocolate chip. So if you're given that we are choosing from jar C, what would the probability of getting a chocolate chip cookie be? So if I was already in jar C, then my probability of chocolate chip is what? 2/3. Okay, KJ, you good? All right, so same idea for this next one. So it talks about how there's 4 blue marbles, 3 red marbles. And then we choose the second one. So we have blue, red, red. Okay. This is called a dependent situation because it depends on what happened on the first one because we're not replacing the original. Okay, do you guys know dependent versus independent? So the first event changes my probability for the second thing. Okay, that's dependent. So it says there were 4 blue marbles, so 4 out of 7, and 3 out of 7 for the red. Okay, once I choose a blue marble, so if I go along this route, what happens here? What's my probability of getting a blue? 3 out of, what'd you say? Out of 6, right? Because there's 1 less. What's my probability of getting a red? There's still 3, right? Still out of 6, right? Okay, what if I go the red route and I pick a red marble for the first one? There's now 1 less red marble, so now I'm down to 2, and 1 less marble in general. So my probability of getting a red is now 2/6, and my probability of getting a blue is 4/6. So that's our tree. So what's the probability of drawing 2 blue marbles? So having a blue and then a blue again. Well, that would be going this route right here. It would be 4/7 times 3/6. Would it be what? Because we drew a blue if we go that route. So if we go this route and draw a blue one first, there's 1 less blue. Does that make sense? Yeah. So we get 2/7. What's the probability in drawing 2 red? So we look at our red one. So we're like, oh, 3/7 for the first one, 2/6 for the next one. I think it ends up being 1/7. All right, does this make sense? Do you guys get it? What about a blue and then a red? So you look at that route. So probability of a blue and then a red. Kenzie, you look confused.
Oh, okay, never mind.
So the blue is 4/7. The red would be what, 3/6? Is that right? So I think that's still the 2/7. Okay, here's the weird part. This is called conditional probability. It says if you're given, so if you're told that your first marble is blue, okay, so that means we're zooming into part of this Venn diagram. We're saying, oh, we know the first one's blue. So then what's the probability that the second one is, what did I say, red? What's the probability of drawing a second blue? 3/6, which is 1/2, right? Okay, so number 3. So assume the probability of the birth of a child of a particular gender is 50%. It's not, but we're going to assume for this problem. In a family with 4 children, what are the probabilities that all of the children are boys? Okay. So if you have 4 children, what's the probability of getting boy, 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 boy? Imagine the tree. You got a really big tree. How many outcomes, how many branches, like if I followed the top, the next, all the way down, how many branches would I have? Let's think about our fundamental counting principle. How many possibilities for the, well, I feel like these are outdated problems. I should update them. So 2, 2, 2, 2, right? So I have 16 possibilities. So there's 1 way to get all boys, so 1 out of 16. So all of the children are the same sex. That would be 2 ways, right, out of 16, which is 1/8. And then there is at least 1 boy. Do I want to count up all those branches? If I talk about at least 1 boy, that's every single outcome except the one with all boys, right? Does that make sense? Or all girls. So it's going to be 1 minus 1 over 16, which is 15 over 16. Make sense? Okay. Oh, gosh. It's the longest section ever. I'm sorry. All right. Out of 40 students, 14 are taking AP language and 29 are taking physics. Okay, so I selected 40 students, AP Lang, and physics. Okay, 5 students are in both classes. So I always fill the middle if possible. If I can't fill the middle, I put an X in there. Okay, so I have 5 in the middle. 14 are taking AP Lang. So that means how many are in AP Lang only and not also in physics? 9. And 29 are taking physics, so I have 24. So I don't know. So how many total do we have right now? We have 14 plus 24 is 38, right? How many are not in either one? 2. So 2 are out here. What's the probability that a student randomly chosen from this group of 40 students is taking only physics? How many are only taking physics? 24 out of 40. I don't know what that is. 12 out of 20. 6 out of, oh man, I should have gone bigger. 3 out of 5. All right, if you're told that they're in AP Lang, here's the weird one. If you're told that they're in AP Lang, so circle here. How many people are in AP Lang? No? 14. What's the probability that they're in physics as well? 5 out of 14, exactly. Good. All right, let me give you your homework. It's not as long as the last one.